Hi guys, Jason Matthew here, and today we're going to be looking at chemical equilibrium. Now, for those who are familiar with my work, you know that normally I produce videos for my biochemistry students at the University of West Indies. But commonly enough, when you do biochemistry, you have to understand basic chemical concepts, and unfortunately, some students still have trouble with these concepts. So I've designed these videos as support for these students who would like to strengthen their chemistry kung fu. This is also applicable to any student who is doing chemistry at the introductory level at university or the A-level students out there. So please have a look. So let's get started. Right, so the classic reaction. When you now start chemistry, you know that you have reactants, and reactants are converted to products. And you see this single-headed arrow here, all right, showing that it goes in one direction. It goes from reactants to products, and there is 100% conversion, meaning that all of the reactants is converted to products, and the reaction goes to completion. However, for most reactions, that doesn't happen. The reaction is what we describe as reversible, meaning that the reaction will go in both directions, both the forward direction as well as the reverse reaction, which simply means that for example, in this example here, A is converted to B, and likewise B will be converted to A. And in a reversible reaction, it will eventually achieve equilibrium, and that's something we're going to be discussing at length today. Now look at the arrows here. So these arrows will show that this is a reversible reaction. You see that they are double-headed, sorry, I should say they are single-headed double arrows, all right, to show that they're going in both directions, as opposed to the reaction we saw before in the previous slide, which just had one arrow going in one direction. So what are some of the features of a reversible reaction? Well, for one, these reversible reactions, they occur in a closed system. So for you to achieve equilibrium, the system must be closed. And what we mean by that is that matter, when equilibrium is achieved, matter cannot enter the system, nor can it leave the system. And this equilibrium is dynamic. It's not static. Dynamic meaning that there are particles that are moving. All right, so microscopic versus macroscopic. Now, at the macroscopic level, in other words, if you had a reaction that was in equilibrium and you were looking at it, you will see no visible change. All right, so at the macroscopic level, when you look at it with your naked eye, you're not seeing any change. But at the microscopic level, where you're looking at particles moving, there is something happening. It's dynamic, there's movement. All right? And there's actually, at equilibrium, there's a specific amount of movement taking place. And we say that the rate of the forward reaction is equal to the rate of the reverse reaction. And if we go back to our example up here where A is being converted to B and B is converted to A, what we are saying is that when equilibrium is achieved, some particles of A will be converted to B at the same rate at which some particles of B will be converted to A. In other words, the same number of particles converted in a specific unit of time is equal to the same number of particles of B being converted to A in that specific unit of time. So the rate of the forward reaction is equal to the rate of the reverse reaction. Now at equilibrium, we are saying that the concentration of A and the concentration of B remains constant. So all we are saying is that at equilibrium, the concentration of A will no longer change and the concentration of B will no longer change. We are not saying that the concentration of A has the same value as the concentration of B. That's a different thing. We are saying that the concentrations at equilibrium are constant. So let's look at this from a graphical point of view. And for the purposes of these graphs, we're going to be looking at the typical reaction A plus B to give you C plus D. Now if we were to follow the concentration of A, alright, and we're looking at the concentration of A and how it changes with time. Now, when we started this reaction, we only had A and B. So the concentration of A would decrease as the reaction proceeds until it reaches equilibrium. The concentration of A remains constant when equilibrium has been achieved. Alright? Now, so in other words, if this reaction was only in one direction, it means that all of A would have been converted, meaning that you would have had a graph where it would have eventually reached the zero mark. But that's not happening, and the reason for that is the reason why this curve will never reach the zero is because this reaction is an equilibrium, is a reversible reaction, meaning that this reaction will never go to completeness. So at the end of the day, if you allow as much time to pass, you will always have A, B, C, and D in your reaction vessel. Alright? In other words, this reaction will never go to completeness where you would only see C and D. You will always have some A and B. Alright? And if we look here, we see that the concentration decreases, and then the curve flattens out. And what this represents here is that the concentration of A is no longer decreasing. It is remaining constant. The concentration is no longer changing, it's remaining constant, it's the same. And we say that in this area here of the curve, this represents equilibrium because the concentration of A is remaining the same. Now let's look at the concentration of D now. Now the concentration of D increases as the reaction proceeds until it reaches equilibrium. At equilibrium, the concentration of D remains constant. So if you look at the graph here, remember at the beginning you only had A and B. So at the beginning of the experiment, at the beginning of the reaction, there will be no D, so D will be 0. But as A and B starts to react together, the concentration of D will increase. But there will be some point in time where this curve is going to flatten out, meaning that as time passes, the concentration of D no longer changes. And we say that when the concentration of D when the concentration of D remains constant, we say that the reaction has reached equilibrium. Now, if you combine the two graphs, you see that after some time, both A and D, their concentration is remaining constant, and we say that this is where equilibrium is achieved. So at equilibrium, the concentration of A and D will remain the same. And similarly for B and C as well, the concentrations of B and C at equilibrium will remain constant as well. So one final thing to look at the graph. So let's read here. The rate of the forward reaction falls with time as A and B are used to form C and D. At the start of the reaction, there is no C and D, but as A and B form C and D, their concentrations increase. As the concentration of C and D increases, the rate of the reaction between C and D increases. At equilibrium, the rates of the two reactions will become equal. A and B will form C and D at exactly the same rate as C and D convert back to A and B. So let's look at the graph here. So again, we are still looking at the typical reaction A plus B to give you C plus D. Right? So in the forward reaction, it will be A plus B to give you C plus D. And the reverse reaction will be C plus D to give you A plus B. And what we're saying is that if you look at the rate, well, initially, there's only A and B in the reaction vessel. So their rate is going to be high at first. But as A and B is being consumed, the rate starts to decrease. All right? And we see here that at a point in time, both rates are going to be constant. All right? They're going to have the same, and they're going to have the same rate. And at this point where the reverse reaction as well as the forward reaction has the same rate, we say that equilibrium has been achieved. So at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction, which simply means that the rate at which A and B is being converted to C and D is the same rate at which C and D is being converted back to A and B. So a very important principle when you study equilibrium is the Le Chatelier's principle. And Le Chatelier's principle states that if any change is imposed on a system at equilibrium, then the position of equilibrium would change in such a direction as to try and remove the imposed change. So let's look at this typical reaction. We have Fe3 plus thyrocyanate, all right, to give you the salt. And the question here is, what would you observe if a soluble Fe3 plus salt is added? And the second question is, what you'd observe if the concentration of the thyrocyanate is decreased? So what you need to do is apply Le Chatelier's principle and see what you come up with. And the key thing here is observe. All right? If you want, you could pause the video now, go back and look at what Le Chatelier's principle is about, and see if you can't answer these questions on your own. All right? So write down something. Write down a possible answer for these questions. And then you can press play again and you'll get the answer from me. All right? So I'm giving you 2 minutes to go and check that out. All right, so let's see if you all got it out. Now let's look at the first part here. And what they're saying is that what would you observe if a soluble Fe3 plus salt is added? So let's look at the reaction. On this side, all right, on this side of the reaction here, if you look at the colors, it's pale yellow, colorless. And on this side, the solution is much darker, it's deep red. So what will we observe? Now if this system is in equilibrium, and remember in equilibrium, we have to use Le Chatelier's principle. And basically what Le Chatelier is saying is that when you are at equilibrium, everybody who is involved in that equilibrium is very happy there. All right? They don't want change. They don't like when you change something there, and they will try to resist that change as much as possible. So for question 1, what is the change that we are doing here? Well, the change is that we're going to be increasing Fe3 plus. All right, so you're going to be increasing Fe3 plus ions here. So that's the change you want to put on this equilibrium. And as I said, everybody in that equilibrium is very happy. So the thing is that if your change is to increase Fe3 plus, then the position of equilibrium will shift in a way to decrease Fe3 plus. All right, so let's recap. Your change is that you are going to increase the amount of Fe3 plus. So the position of equilibrium will react in a way as to shift in a way that will reduce Fe3 plus. So to reduce Fe3 plus, it means that it's going to react with the Fe3 plus you added with the thyrocyanate ion to give you this. So if you had this system set up in your lab, what you would observe is that you will see that the color of the solution in the beaker will start to get darker because more of this guy here is being formed. Now that we have done this one, in case you didn't get that first one right, use the same logic that we just worked out for this guy and see if you can come up with an answer for question 2. So I'll give you 2 more minutes just in case you didn't get the first one right. I'm giving you a second opportunity now to get this second part right. So take 2 minutes. Right, so I'm hoping that you got this, you're going to get this correct. The change that we are going to impose on this system is that we are going to be decreasing the thiocyanate ion. Now, as I said, at equilibrium, everybody's happy. Now, if your change is that you are going to decrease thiocyanate, then the position of equilibrium will shift in a way that will want to increase thiocyanate. So to increase the concentration of thiocyanate, the position of equilibrium will now shift to the left, meaning that some of this is going to then form more thiocyanate ion. So if you had this experiment set up in the lab, you'll see that the solution in the beaker will be getting lighter in color because more of the thiocyanate and the Fe3 plus is being formed. So it's going to get lighter in color because you'll have less of this now. All right. So let's recap. So when we added the Fe3 plus salt, the position of equilibrium shifted to the right. In other words, the forward reaction was favored. All right, and that made the solution get darker. When we decreased the concentration of the thiocyanate ion, the position of equilibrium shifted to the left. In other words, it favored the reverse reactions, so the solution in the beaker got lighter in color. Right, so there are a few things that affects the equilibrium. We already looked at concentration. Now we're going to be looking at temperature, and then we're going to be looking at pressure. So we're looking at the effect of temperature on equilibrium. So it goes like this. Any change in temperature will alter the value of the equilibrium constant for the reaction. All right, so temperature does two things. One, it actually changes the value of the equilibrium constant. Concentration doesn't do that. Right? But temperature will actually change the value of the equilibrium constant. The other thing that you need to know is that in any reversible system, an increase in temperature favors the endothermic reaction, and a decrease in temperature favors the exothermic reaction. So a few things here. You need to know what endothermic means. All right? So for those who are versed in their thermodynamics, they would know that endothermic reactions are reactions where delta H is positive. All right? So for endothermic reactions, delta H is positive. What that simply means is that the reaction is going to absorb heat. And for exothermic reactions, delta H is negative. And what that simply means is that in an exothermic reaction, heat energy is released to the surroundings. And you can see that. You can see why that makes sense here. Because if a system is in equilibrium and you were to increase the temperature, so that's the change you're going to make, it means that the position of equilibrium will shift in a way that you want to absorb that heat that you just added. So you would want to favor the endothermic reaction, which will absorb the heat that you just added. Similarly, if you were to cool down the reaction, all right, so this reaction is in equilibrium, and you decide to cool it down. So in other words, you are decreasing the temperature. Then the position of equilibrium is going to shift so as to minimize that decrease in temperature. In other words, to increase the temperature once again. So what you do, it will favor an exothermic reaction which releases heat energy. So it's always, with Le Chatelier's principle, the position of equilibrium is going to oppose anything you do. So if you increase temperature, it's going to favor an endothermic reaction so you could absorb and bring back down the temperature. If you decrease temperature, it's going to favor the exothermic reaction, which is a reaction that releases heat, so the temperature will go back up. All right, so it always opposes what you do, and the reason for that is because it's very happy where it is. Why are you coming and trying to produce change on them? All right? Right, so this is a general term here, heterogeneous versus homogeneous. All right, and it has to do with the different phases. You have gases, liquids, and solids. And for homogeneous reactions, all the reactants and products are in the same phase. while for heterogeneous reactions, reactants and products are in different phases. So that's something to remember. Right, so the effect of pressure on equilibrium. And it goes like this. If the total number of gas molecules on each side of the equation differs, then any increase in the total pressure will cause the system to move towards the side which has fewer molecules. Likewise, any decrease in pressure will result in the system moving towards the side containing more gaseous molecules in order to keep Kp constant. So this would make sense if you know a little bit about your physics and the gas laws and so on, or kinetic theory, I should say. And you know that the more gas particles you have in a system, the higher the pressure. So let's apply the calculus here and see if this makes sense. Your change to this equilibrium system is that you are going to increase the total pressure, right? So let's remember by the calculus what the percent equilibrium will do. It will shift in a way to lower that pressure. So in other words, it's going to go to the side that has fewer gas molecules, because the side with the fewer gas molecules has a lower pressure. And if you understand that, then you can understand the second half, because it's basically the opposite they're looking at here. So let's look at a real life example here. And this is the production of ammonia. All right. And you see, well, first thing to always check when you're looking at pressure is to look at the state symbols. All right. Because it's only gas molecules you really want to look at when you are talking about the influence of pressure on the position of equilibrium. So the good news here is that when we look at this whole reaction, all the components are gaseous molecules. So the nitrogen is gas, hydrogen gas, ammonia gas. So everything is gas. So all these molecules here matter. So the next step you do is that you count the amount of moles of gaseous molecules on each side. So you have, well, our 1 is understood here, so it's 1 plus 3. So you have 3 moles of gaseous molecules on this side. And when you go over on this side, you have 2 moles of gaseous molecules. So that's the next thing. Because the numbers differ on both sides, it means that an increase or decrease in pressure is going to affect the equilibrium. So remember, an increase in pressure will favor the forward reaction in this example here. Why? Because if you increase pressure, the position of equilibrium is going to shift to where there is less gas molecules. In this case, it will be this side. All right, so you see here, the position of equilibrium will shift to the right. So you're going in this direction here. So it means that you're going to get an increase in ammonia if you increase the pressure. Now likewise, all right, if you apply the same concept here, a decrease in pressure, all right, for this example, if you decrease the pressure, it's going to favor the side with more gas molecules, because when the position of equilibrium shifts to the left, in other words, it favors the reverse reaction, you're going to have more pressure because you have more gaseous molecules on this side. All right, so it's always to oppose whatever change you apply to the system. Now, the use of catalysts in reversible reactions. A catalyst does not affect the equilibrium constant, but enables the equilibrium state to be reached more quickly. And this is important because this applies to both inorganic catalysts as well as biological catalysts. So when you do enzymes, that's a very important point to remember, that enzymes do not affect the equilibrium constant. So when you're deriving your various equations and stuff for enzyme kinetics, remember that the catalyst, which in that case would be the enzyme, it does not affect the equilibrium constant. So let's read the second part here. Simply speaking, a catalyst provides an alternative reaction pathway with a lower activation energy. The activation energies of both the forward and reverse reactions are reduced by the same amount. As a result, both reactions are speeded up by the same factor, and so the equilibrium constant does not change. And as I said, this you will also learn when you do enzymes. So if you learn it now, it will be one thing less to learn when you study enzymes. So now let's look at some real-life examples here. All right, let's apply the knowledge that we just learned about equilibrium to some industrial processes. So the first one we're going to be looking at will be the Haber process. And the Haber process is the industrial manufacture of ammonia. So we are already very familiar with this equation here because we looked at it before. All right, so we're using back the same equation here. And we see that in the industry, they normally use 250 atmospheres, 450 degrees Celsius, finely divided iron coated with potassium oxide and aluminum oxide as promoters. So it means that this finely divided iron coated with potassium oxide and aluminum oxide, that would be the catalyst. Now you see I put in red here, compromise, because this is an industry. So when you are designing your production plant, you have to take into consideration both the chemistry as well as the economics. So let's see. So there's always a compromise between the two. So let's see if we would what would happen if we just apply the equilibrium, our knowledge of equilibrium alone. So we already saw that our goal here is that, remember, this system is a reversible system, meaning that they will always have nitrogen gas, hydrogen gas, and ammonia in the final reaction mixture. The whole thing here is that for us to make more profits, our goal is to maximize the yield of ammonia. So you want to get as much ammonia as possible. And the conditions we use will be key to that. So you remember, or you should remember from the previous slides, and if you don't, go back, that if you increase pressure, you're going to get a higher yield of ammonia. Now, 250 atmospheres is a very high pressure, and you normally get a yield over 90% of ammonia. But why is it that probably somebody else who's building an next plant doesn't think and say, well, hey, well, if 250 atmospheres give me 90%, let's use 500 atmospheres, so we get even more, a higher yield. Why is it that all these Haber process plants, production plants, why do they always stick around 250 atmospheres? The thing is that, as I said before, you have to also consider the economics behind it. Because to get 250 atmospheres, it means that you have to use compressors, all right? So you have to use pumps and so on to create or generate this high pressure. And those compressors would require a large amount of energy. So that's a cost there, all right? As well as the reaction vessel itself will have to have thicker walls so it can sustain such high pressures. So you also have a cost factor there as well. So they have come to a compromise at 250 atmospheres is good enough. 90% yield, we can make enough money out of that kind of yield. So we are happy with 250 atmospheres. Now the temperature, 450 degrees Celsius. Let's see if this temperature correlates with what we know in equilibrium. So if we are just applying equilibrium knowledge alone, we have to look at the equation here. And to know if a high temperature is going to favor the forward or reverse reaction, you need to look at, you need to look at the delta H value. Now the numerical value isn't important for us. It's actually the sign. So if you see in this reaction, delta H is negative. So if I tell you a reaction is delta H is negative, is it an endothermic reaction or is it an exothermic reaction? And if you can't confidently answer that question, you need to pause now and go back and learn that, because that's a fundamental piece of thermodynamics, and we actually mentioned it in the earlier slide. So you could go back and see what the answer is to that before we go forward. All right. So now everybody should know that when you see delta H being negative, it means that this is an exothermic reaction. All right. So the forward reaction In other words, nitrogen gas combining with hydrogen gas to give you ammonia, that's an exothermic reaction. Now, if you remember from before, all right, what would favor of the forward reaction? In other words, when this is in equilibrium, how could you increase the yield of ammonia? Right? Would it be that you have to increase temperature or lower the temperature? All right. So you should remember from the slide before that the lower the temperature is going to favor the exothermic reaction. Right? Now that seems kind of strange because they are using 450 degrees Celsius. And 450 degrees Celsius doesn't by no means sound like a low temperature. And that's because you also have to take into consideration the kinetics of the reaction. So while using a temperature, let's say 100 degrees Celsius, might give you 94% yield, while 450 degrees Celsius will give you 90%. So you might say, hey, I want that extra 4%. The thing is that if you remember from your kinetics, for every 10-degree rise in the for every 10-degree rise, the reaction rate doubles. In other words, that although you might be tempted to lower the temperature, it means that the rate will be significantly slower. And if you're making ammonia, it could be a difference of at 450 degrees, you might get the ammonia at the end of the week. But if you use 100 degrees, you might get at the end of the month. And you can see why that will be a problem if you want to sell ammonia, right? It's better to wait at the end of the week than to wait for until the end of the month, all right? So why do we go through the trouble of making ammonia anyway? And you'll see here that ammonia forms the basis of the nitrogen industry. It will react with acids to give ammonium salts. It can also be oxidized to nitric acid, which in turn can give nitrates. Both ammonia salts and nitrates are used as fertilizers. Ammonium nitrate is also used in the production of explosives. Another industrial process, which is also an equilibrium reaction, is the contact process. And the contact process is the manufacture of sulfuric acid. Now, the first reaction in the contact process is where you react sulfur dioxide gas plus oxygen gas to give you sulfur trioxide. So this is the first step in the production or in the industrial production of sulfuric acid. So once again, we use a temperature of 450 degrees Celsius, approximately 1 atmosphere, and we use a catalyst of vanadium 5 oxide, or you might see in some textbooks it's called vanadium pentoxide. So most of this, in terms of the conditions and stuff, will be the same as before with the Haber process. You're always doing a compromise between equilibria, kinetics, and then the economics is the most powerful driving factor here because it's an industry and you want to make money here. So if you understand the Haber process, you should be able to understand why we are using these conditions for the contact process. Now something in addition, if you look here, you see that we are using oxygen. Now, in order to reduce costs, normal air, because it's used rather than pure oxygen, because that's expensive. While air, at least for now, is free. All right? An excess of air is employed at a pressure only slightly above atmospheric, and it tends to push this reaction in the forward direction where sulfur trioxide is being produced. Now, sulfuric acid is one of the most widely used chemicals. It is required for the manufacture of fertilizers, paints, fibers, detergents, plastics, dyes, and steel. So a recap. Let's see if you all remember the stuff that we have covered so far. So the question here is concerning the following equilibrium above. What would happen if you increase the concentration of D? And the second part of the question is if you increase temperature. Alright, so I'm going to take some time now, pause the video, and actually try to do this question on your own because we have covered the information. You are ready to do this question. And if you think you're not ready, just go back. Alright, go back, look at the slides before, and write down something. I always tell students the most efficient way in learning is that you have to write. All right, so you write what you think is the answer and then compare it to what I'm going to say next. So take a few minutes, go get your pen and paper and write down what you think the answer should be. All right, so let's see. The first part of it is that you are increasing the concentration of D. Now remember in Le Chatelier's principle, if the change you're going to make is that you're going to increase D, the system is going to react, the position of equilibrium is going to shift in a way to oppose that change. All right, so your change is that you're going to increase D, therefore the position of equilibrium is going to shift so as to oppose that change. In other words, it wants to lower D. And to lower D is going to favor the reverse reaction. All right, so for this one here, as you would rightfully, hopefully said, was that it's going to favor the reverse reaction. In other words, the position equilibrium will shift so that C plus D will react to give you A plus B. All right? Now, the next piece of the question here now, if you increase temperature. Now, to answer that question, you need to know the delta H. Not so much the numerical value, but the sign. All right? So if you have delta H is positive, what does that mean? All right? And it should be correctly said as it's an endothermic reaction. All right? Now, the good news is that if the forward reaction is endothermic, and an endothermic reaction is one that absorbs heat, if you are the change that you are opposing here is that you are going to increase temperature, meaning that you're going to increase the amount of heat there, then that is going to favor the endothermic reaction, which is the forward reaction. So it's going to favor the forward reaction, which in this case is A plus B to give you C plus D. Now, I should have really balanced these things off. Alright? So, that's something else to note. Right, so now we have a second question here. This one is about pressure. Concerning the following equilibrium above, what would happen if you increase pressure? Now, there's a trick here. So, please, again, you know the drill. Press pause. Alright, go back to the previous slides if you have to go pick up your textbook and so on, and try to answer this question on your own. So write down an answer. I'll give you a few minutes. I'll be right here waiting for you when you are finished. Oops. Alright, technical error there. Alright, so concerning the following equilibrium above, what would happen if you increase pressure? Now remember, the whole trick here is all about state symbols. I hope you noticed that, right? You're only dealing with gaseous molecules when you are talking about pressure, right? So anytime you're dealing with pressure, it's only the molecules that are in the gaseous state. So it means that C is out, A is out. Right? Don't worry about that. As well as this information here will not help you in your question at hand, which is to what will happen if you increase pressure on this equilibrium. So the only two pieces of information that is required here is the amount of molecules on this side, gaseous molecules, and the amount on this side. So you have one molecule on this side, one mole of gas, and you have 2 moles of gas on this side. So if you increase pressure, if you remember from your notes before, if you increase pressure, it's going to favor the side that has less moles of gaseous molecules. So in other words, for the answer for this question is that it's going to favor the reverse reaction, because on the reverse side, there's less moles of gas. So that is what you were supposed to be careful about. The trick here was to only focus on the gaseous molecules. So I hope you got that right. If not, don't panic. Just go back to the slide before and just recap. And probably just need to do it once or twice. Alright guys, so I hope this was very informative for you. We have other videos on our channel, Biochem Gems, so please go have a look. Alright, if you like what was happening, you can show your love by clicking the like button, as well as subscribe to our channel. And we would love to hear your comments, so please, give us your comments, tell us how we could improve your learning experience. Alright, we love to hear from you guys. And as usual, I just want to say thank you for taking time to listen to this video, and I hope it really helps, and good luck with your future studies. Take care.